All right, so we're going to start our unit on vectors. We'll spend about 4 days on it, as I said. So we'll split it into 4 parts. Everything we do on vectors will be in a different book. So I gave you a packet. The packet I think I gave you, it says 5.4 for what we're doing today. 5.5 will be the next packet. Then 5.6, something like that. So the other book I have splits what we're doing into different sections, which makes it a little easier. Your book just has one big section on vectors, okay? But we really need to split it up. So some people mentioned that they're already looking at or studying vectors in physics. Can anybody tell me what a vector is? It measures 2 things at the same time. Mm-hmm.
It measures a magnitude and the other one, I think it's like trajectory, right?
Okay, so I definitely like magnitude. Could we kind of narrow down that word trajectory, what that means? It's the, not a distance. It's a direction, yeah. So a vector is used anytime you want to model something, basically things that move, or forces, either way. You want to model something that has a magnitude and a direction. Can anybody think of something in real life that has magnitude to it and a direction to it? Yep. Adrian?
The tornado.
A tornado?
I think it was an earthquake.
An earthquake? Yeah, earthquakes, I know what you mean. They have like a magnitude to them.
Yeah.
The only thing about an earthquake is it usually radiates out in all directions. It doesn't just have a single direction. Like a tornado might, but the direction might also change with a tornado. It could go different ways. We're trying to think of things that always stay in the same direction for the length of time that it's moving, generally, just to keep it simple. Yep.
How about a rocket?
Yeah, like a rocket. Okay.
Do you mind if I borrow this? I just need a pencil.
So a rocket has a, well, assuming once it gets up to speed, it stays going at the same speed. Okay, so it has a magnitude and it has a direction. That's a more specific example of really what we just call velocity. Anything moving, whether you throw an object, drop an object, a rocket, things like that, that's all examples of velocity. And then force is another example of a vector. Okay, so force, basically if you push on an object, right, you might have a certain strength of how hard you're pushing on it, and you might be pushing in a certain direction. Okay, pushing down with a certain amount of force is different than pushing left with a certain amount of force. Okay, it's different. And an example of where it's important to kind of keep track of vectors is when you're dealing with airplanes. So this website basically shows you some of the airplanes that are in the air right now. And if we click on any one of them, they all have different speeds. Keep in mind this is 3-dimensional too, so they might be at different altitudes, but just look at it as being flat. Okay, they all have different directions and different speeds. So near the airport there's the tower, and it's controlling all the traffic in that area, making sure that the planes are all on different courses and they don't hit into each other. So you can really think of airplanes as just a bunch of vectors on the screen. Right, so that's an example where they might use vectors. Yes?
What's a vector?
Yeah. So what's that? You can see the whole country, but if you zoom out enough, the planes just, they cover the whole thing because the country gets like this big.
Let's see it.
So then the planes just cover the whole thing. So if you just zoom out a little bit.
DC.
So there's a lot of airplanes.
I think DC has.
They're in New York.
At least for Trump's day,
Trump's.
So yeah, and that's probably not even the busiest. If you go down to like Atlanta, Georgia, that's another huge airport. It probably has a lot more traffic. Not sure
We
we.
have that many planes in the air.
So many people
That's Florida.
Florida's in there. Georgia, I can't quite see somewhere in there. Maybe that's.
That's probably later.
Yeah. So all of these planes have different vectors, and it's the job of computers and people to kind of make sure that they're all on different approaches and things like that. So one way we can represent a vector is by drawing a picture of it. And we use an arrow. And an arrow can represent two things at the same time. First of all, you can draw the arrow a certain way, so it can point in a certain direction. And the length of the arrow can represent the magnitude. So both of these vectors in blue have the same direction, but they have different magnitudes. Now, there are some disadvantages with drawing things visually like that, as far as doing basic arithmetic with vectors. Drawing pictures is time-consuming. Where pictures do come in handy is word problems. So if you have a word problem, it helps to draw out the pictures. So sometimes we'll draw pictures, but eventually we're going to also come up with another way to represent vectors that are non-visual. Okay, it's still visual. You write something down, but it's more you're writing numbers down rather than drawing arrows. So any question on how you can represent a vector as an arrow? Or it's a ray, like from geometry. All right, so when we draw a vector has 2 points. It has what we call an initial point and a terminal point. The initial point is where the vector starts. The terminal point is where it ends. So just like in geometry, if you describe this as ray PQ, this is how you would probably describe it in geometry, ray PQ. This is not the same as saying ray QP. They're not the same thing. What would be the same about ray PQ and ray QP? The magnitude would be the same, but the direction is exactly the opposite. Okay, we don't really use that notation very much. That's more what you'd use in geometry. But if you want to kind of connect what we're doing with something in geometry, that's the connection you could make. A lot of times when we want to represent a vector, we use a single letter. So for example, I could call this vector M, or X, or Q, or whatever letter I want to call it. And there's 2 ways I can describe it if I want to write it as a letter. If I write it just like that letter I have M in blue up above, to me that just looks like a variable. So I have to distinguish it from a variable that you'd see in an equation. There's 2 ways to do it. One, put an arrow over it. So now you're telling me that this is vector M. That's the name of it. Or, if you don't want to put the arrow over it, you can make it a bold letter. Bold letters are also used to represent vectors. Okay, in your textbook, or in the handout I gave you, if you look at it, they do use bold letters to represent vectors. You look at all the formulas on page 335 in that packet, they use bold letters all over the place under the section that says adding vectors. So any questions on the 2 ways that you can represent a vector as a letter? Okay, either put an arrow or use a bold letter. All right, so first idea we want to kind of understand is what happens when you add 2 vectors together. Well, think of it as like combining 2 forces. Let's say you're pushing to the right on an object, and then somebody else comes along and pushes up on the object. What would happen if you push right and the other person pushes up? What direction would the object move in?
Up, right.
Yeah, it would be moving up and to the right. It would be moving in a new direction. with a certain magnitude to it, with a certain amount of force behind it. Well, if it's moving in a new direction and it has a magnitude, it's a new vector. Okay? Another example would be, think of an airplane flying. If an airplane is flying south and there's a wind blowing 100 miles an hour to the east, coming from the west, blowing to the east, is that plane really going to be going straight south? No, because the wind, think of that as a vector. It has a force and it has a magnitude, 100 miles an hour blowing, what did I say, east. It's going to blow the plane off course a little bit. So the pilot would have to correct for that. If the pilot doesn't, the plane is going to go in a new direction, and the speed of the plane could change. If the wind is coming from behind the plane, it would speed the plane up. If the wind is coming in front of the plane and the pilot's flying into the wind, it not only might change its direction, but it might slow the plane down. Okay? So whenever you combine two vectors together, like wind and a plane, or two forces working together, we get a new vector. So what we're going to do is look at how we can add vectors visually. Okay? And basically the idea of what you do is, let's say this is V, and let's say this is W. In order to add them together, I take V and I put W on the end of it, just like that. So I'm basically connecting where the end of V is to the beginning of W. And then I would draw a new arrow from here to there. Okay. What I just did in red, that is V plus W. Okay. So how did I do that if you want me to describe it in words? Okay. You have to position V and W just like I have them up above, so that the ending point of V, which is right where the tip of the arrow is, lines up with the initial point of W, which is where the arrow starts. Okay, so the ending point of V lines up with the beginning point of W. And then once you do that, all you have to do is draw a new arrow from where you started, and just follow the direction of the arrows to where you end. That's it. And that's V plus W. Okay, and you can do that with as many vectors as you have. Like, let's say you had a third vector you wanted to add onto the end of that one. Right, well, I would just put that one on the end like that. Okay, so the direction of the arrows, it's one way. They should all follow the same path. Think of it as like, fluid through a pipe or something. It's all going in the same direction. You would never have something like that, because now you've kind of broken the flow of the arrows. Okay, it should all flow the same way. And then you just connect where you started to where you stop. Okay, and that's how you add vectors visually. It's a lot easier to just show you. That's why I did the picture first. The description of it, there's just not really a shorter way to say that. So. Any questions on how to add vectors visually? Right, so let's look at an example. So you don't really need graph paper. I just use graph paper. But I'm going to take V, and I'm going to add W onto the end of it. So for your purposes in your notes, you could just draw V roughly the way I did and draw W kind of like I did. On the test, you'll have graph paper, so you can be more precise. So I'm going to just take V, put it right there. I'm going to take W, put that right on the end of it. And then I'm going to connect where I started to where I stopped. And that's V plus W. Okay, so let's draw our arrow. And that's it. You can't really see the arrowhead. If I just move it down, then you can see it better. All right, and then just label what it is. So this is V plus W. When I'm writing things out, I usually use the arrows on top because bold letters, they kind of take a while for me to make them bold, so I just put the arrows. Any questions on V plus W? So if these were two forces, like a plane flying in a certain direction and the wind blowing, the plane is would be flying with the wind here. Because let's say the wind is this arrow, right there. The wind is blowing to the east, and the pilot is kind of trying to travel to the east anyway. Not directly east. The pilot's also trying to fly south a little bit too. But the wind is going to kind of blow the pilot in the direction he wants to go anyway. So it's more of a tailwind than a headwind. All right, let's look at what happens here. Anyone think they can tell me what's going to happen when I add these up?
Nothing go anywhere.
Yeah, what's going to happen is we take the ending point of V and connect it, take the ending point of V and line it up with the starting point of W. And then once you do that, you want to connect where you started to where you're going to stop. So once I line up the red dots, then I need to connect the blue dots. Okay, so watch what happens here. Lined up the red dots. Now if I connect the blue dots, they're the same dot. So I can't draw the answer to this one. But when I add two vectors, the answer is always a what? We just said this. It's always a new vector. Okay. This answer is called the zero vector. It's the only vector that doesn't have a direction, and it doesn't have a magnitude.
Aren't some vectors like more forceful than others though? So let's say I'm a pilot and I'm flying in the direction and the wind's blowing in the other direction. That doesn't necessarily mean that I'm just going to stop midair as a pilot and just fall back to the earth, because I have more thrust behind the back of my plane than the air has thrust against my plane, right?
Yep. So in this particular case, the two vectors were the same, but you could definitely have one like this, where maybe that black one is your plane, and, well, they're both black. The bottom one is your plane, and the top one is your wind. So in this case, you have more power, so you will overcome it, but it's going to slow you down. Yep. So just because two vectors go in the opposite direction doesn't mean they always cancel out. They would have to be equal in magnitude to cancel out, like they are in this case. Okay, and the answer here, this is called the zero vector. So that's what you'd write for your answer, zero vector. Not zero the number, because when you add vectors, you don't get a number. Okay. All right, so we're going to take a look at how vector addition is commutative and associative. Basically, if you write this down, that's all you really need, because it's kind of hard to show in your notebook what I'm about to show on the smartboard. So I'm going to take V plus W, and then I'm going to switch it and do W plus V, okay, and show you I get the same thing. So here's V. I'm going to add W onto the end of it, just like that. So now, that line that I just made, that is V plus W. Any questions on V plus W? Okay, now I'm going to switch it. I'm going to take W and I'm going to add V onto the end of it. That's not the same thing I just did. Okay, the vectors are in a different order. Now, I'm going to draw a line from where I started. Let's see, I was a little bit off, but that's pretty good. From where I started to where I stopped, and if we go and compare it, it might not be perfect because I didn't use graph paper, but it's pretty close. Okay, so what I'm basically just showing you there is v plus w is the same as w plus v. So the order you add vectors in, it doesn't make a difference. And vector addition is also associative. I'm not going to go through and show this one, but associative is basically the idea of I could add A and B first and then add C onto the end of it. Or I could add B and C first and add that onto the end of A, and I would get the same thing. Okay, you've done the same thing with numbers, like 1, 2, and 3. Okay, so that associative property that you know for numbers, it works exactly the same for vectors. Okay, I'm just not going to go through and show that one. So any questions on the associative property or commutative property? All right, and those are the vectors I would use if I was going to show it. Okay, what's the difference between the two things I have up there? So what would that do to the vector? It would change the direction. Can you be more specific in how it would change it? It'd be exactly the opposite. It's like it would be a 180-degree rotation. What doesn't the negative change about a vector? It doesn't change the magnitude. So that's what we just said. So we saw this idea earlier. I didn't write it like this, but if you take a vector and add its opposite, in other words, the same vector, just pointing 180 degrees the opposite way, the two vectors cancel out, and the answer that you get is the 0 vector. Okay, I don't know if anybody noticed, but I didn't have the arrow on top of the 0 when I first showed the slide. That was wrong. You don't get 0 number. You get the 0 vector. That's why I added this arrow. Okay. Any questions on that idea? So, if we know that a negative vector is exactly the same thing, all you have to do is reverse the direction, we can use that idea to subtract vectors visually. Okay? And we can subtract vectors visually the same way we added them. I want you to tell me, what's another way you could write 3 minus 2? Doing it with addition.
3 plus negative 2?
Yeah, 3 plus the opposite of 2. So if I wanted to take vector v and subtract vector w, instead of doing it that way, how could I do v minus w as addition? Yeah, take vector v and then find the opposite of negative w and add them. That's how you do subtraction. Leave the first one alone, find the opposite of the second one, and add. And that's really doing subtraction. Okay, so to subtract two vectors, find the opposite of the second vector and add. Okay, so let's try an example where we subtract two vectors. Okay, I want to find v minus w visually. So I'm going to think of this as v plus negative w. So what's the first thing that I need to find here if I want to do this?
The reverse of W.
I need the reverse of W. And on the smartboard, I can do that easily by doing a flip twice. I need a copy of it. And then if I flip left, right, and I flip up, down, it exactly reverses it. Okay, on paper, if you had grid lines, you could just measure it and do it that way. All right, so now I take V, and then I'm going to add on to the end of it negative W. So what I'm finding right here is V minus W, because I'm adding the opposite of W. I can't quite, just because of the angle of the lines, I have to kind of draw this one the best I can by hand.
Pretty good shape.
Yeah, thank you. So there's V plus negative W. Okay, so questions on how to do subtraction. Let's find the opposite of the second vector and then add. Okay. All right, let's look at multiplication. Okay, there's a couple different ways we can multiply. Today, we are not looking at multiplying a vector times a vector. That's another section we're going to spend, that's a whole section. We're going to look at multiplying a vector by a number. Anyone think they know what the difference would be between 3v and v? That's an example of scalar multiplication. What's going to be the difference between 3v and v? John? Yeah, it's magnitude. This is going to have triple the magnitude, but it's going to have the same direction. Okay, so when you multiply a vector by a number, that number that you put in front of the vector is called a scalar, because it scales the vector. And when you multiply by a scalar, you get a new vector. Now, this particular scalar that I put in front of v up above, what did this do to the vector? It what? So visually, how would it look? Longer. This particular vector this particular scalar made the vector longer. What else could a scalar do? You could make it shorter. And there's one more thing it can do. How could it reverse the direction if it was what? If it was a negative. So a scalar can shorten, lengthen, or if it's a negative, it can reverse the direction by 180 degrees. Okay, let's look at an example of how we would find 2v given v. Well, if I want 2v, how could I do that visually? Just taking this vector.
You double the size.
Yeah, just double the size. So really all I'd have to do is take a v and then make another copy of it and put them together, and I just doubled the size. So just draw that. And there is the vector. If I move those away, that's the vector 2v. Now, half v, I can't quite do that as easy on the smartboard. I just have to estimate. Half v basically means half as long, but still the same, what?
Direction.
Same direction. Okay. So there's half v. All right, negative v, we already did that, like multiplying a -1 in front. What is that going to do?
It's just going to turn it around.
Yeah, it's just going to take the same vector and turn it around. And then what would -1/3 v do? Two things.
It's going to turn it around.
Yeah, it's going to reverse the direction of it and make it 1/3 as long. 1/3 as long, yeah. 3 times shorter. So, any questions on doing example 5? Okay, I'm gonna hold off on that one. All right, let's just do the second one. 2v minus w plus u. Now, think of these arrows as kind of the building blocks to what I need to do. I'm missing a building block I need to figure this out. I'm missing the negative w. Okay, I need that.
And 2B, you need a double.
Well, yeah, 2v I can construct it by using a v and a v. But I have no way to construct a negative w unless I take w and flip it around first. All right, so I'll take that, flip it left, right, flip it left, down. Now I have negative w. So you can start anywhere you want. Take v. Take another copy of v. That's 2v. And what am I going to add onto the end of that? Put the negative w on the end. And then what goes on the end of that? U. So again, notice the flow of the arrows. They're all the same direction. And just connect where you started. It's a little bit off, but I think it's, I'll just try to fix it like that. All right, that's pretty good. There's 2v minus w plus u.
So on the test, are we gonna have like coordinates that we plot and then we're like?
I might ask you for like an initial point and a terminal point, something like that, or I might give you a multiple choice question and say, if you did this, which of the following would be correct? So I'd give you that as a choice. I might give you the opposite of that as a choice, and things like that. So it'll be pretty obvious there's only one correct choice. All right, so this symbol, when you put double bars around a vector, this symbol means magnitude. Okay, so when we see that symbol in the rest of the lessons we're going to do after this symbol strictly means what is the magnitude of the vector. And the thing about magnitude is because the magnitude is, it's a number that represents how strong of a force it is, or how fast the object is moving. The magnitude is always a positive number. It wouldn't make sense to say negative force or negative speed. Negative is taken care of by direction. If you mean traveling the opposite way, that's direction, not negative speed. Okay? What would be the difference between those two quantities? Nothing. Those are the same thing. What would be the difference if you took away the bars between between just vector v and negative v? Well, if you took away the magnitude bars. Yeah. These vectors are pointing in different directions, but as far as magnitudes, they're the same. Okay, so these two things are the same. Okay, if you have a vector that happens to come out exactly 1 unit long, like a lot of things that come out 1, we use the word unit. Like a circle with a radius of 1 is a unit circle. A magnitude that's 1 unit for a vector, it's called a unit vector. Any questions on what a unit vector is? All right. So I think this is the last thing. So if we're going to start to do algebraic operations like adding and subtracting vectors, visually is okay, but it's kind of time consuming. So we want a better way to represent a vector besides having to draw arrows every time. Okay. And one way we can do that is called an algebraic vector. And it looks just like this. You have this angle bracket, 2 numbers, and then another angle bracket. There's an actual example of one. That's the vector 2, 3. Okay? And those 2 numbers basically tell me how to draw the vector. Okay? A is what we call the horizontal component. Think of it as like your left and right, your x. And B is the vertical component. Okay, so I'm not sure if you need to write the stuff that's from here down, if you understand what I just said. Okay, so A tells you left and right. Start from somewhere, go left and right a certain amount. And then B tells you how far up and down to go. That's the vertical component. And I already said that. A is horizontal, B is vertical. The one thing it doesn't tell me is where to put it in the plane. So for example, if I wanted to draw the vector 2, 3, I could start here and go right 2, up 3, and that's perfectly correct. I could start here and go right 2, up 3. That's also the vector. But where do you think a common place that we start from is? Yeah, a lot of times we start from the origin. Right 2, up 3. Okay. And if a vector starts at the origin, it's called a position vector. Okay, and that's going to be the last thing we do, is how do we find a position vector? Just by looking at a picture or given some information. Okay, so a position vector has its initial point at the origin, and that's what makes it a position vector. Okay, to find a position vector, that's your formula. What they'll do is they'll give you a problem just like the one I have right there, example 7. Find the position vector. They give you an initial point. They give you a terminal point. All you have to do is plug the initial point and the terminal point into the formula that I just put a blue box around. If they don't tell you which one is initial and which one is terminal, assume P1 is initial, because 1 comes before 2. This P2 would be terminal. So this would be like your x1, y1, x2, y2. So let me fill in these two coordinates into that formula. Okay. What is x2 in my example? 4. Minus, what's x1? Negative 1. What's y2? 6. Minus, what's y1? 2. We got to simplify that a little bit. What's 4 minus minus 1?
5.
And 6 minus 2? 4. That's the answer they're looking for. That's it. Any questions on how I found that position vector? So that means if you wanted to draw this vector and start from the origin, you would start at the origin, go 5 units right, 4 units up, and it would be exactly the same picture as what they gave you to start with, except it would start at the origin. Okay, so the homework, remember, it's in the packet. Okay, it's not in the book. Okay, page 344. 1 to 10 all. 14 to 22 just the evens. And 26 to 32 evens. Now on 26 to 32, if you read the directions, you're going to get confused because they're asking you to do something I haven't taught you. On 26 to 32, all I want you to do is find the position vector. That's the last example we just did. They're going to say something about i's and j's. Don't worry about that. Okay, so I'll be after school today for a little bit. Don't forget our test is tomorrow. Okay, and it'll cover everything from 8.2 to 8.5 part 1. Just this week, not last week.